Welcome to Presentation 6. The agenda for today will be external interrupts. External interrupts are part of the layer 2 of our architecture, as you can see it right here. So let's start with some definitions. Let's assume that the microcontroller is connected to an external sensor. An external interrupt can be used to respond to a change on that specific pin. The interrupt will allow the microcontroller to pause its current task and execute an interrupt service routine when a change in the state is detected on that pin. Interrupts enable the processor to promptly respond to events demanding immediate attention, eliminating the need for continuous checking. The microcontroller can configure to trigger interrupts in response to the following signal levels. Low level, any logic change, that means from high to low or low to high, falling edge, or rising edge. Rising edge would be from low to high, and falling would be from high to low. So let's look at the data sheet and see and get some information. Our first step is to go to the ATMEGA 328 data sheet. From this data sheet, we need two pieces of information. The first one is the information associated with the registers, and the second piece of information we need is the information associated with the interrupt service routine, the ISR. So let's go to section 17 and see the information with respect to the registers. So we head to section 17 and then we click on the subsection register description. As you can see, in this subsection we have all the information we need to create our framework. There are a total of 8 registers associated with external interrupts. Next, we need the information about the interrupt service routine. Now, section 16 has a table which includes all the ISR for internal and external interrupts. So we need to, in this section, we need to identify which vectors are associated with the external interrupts. So in our case, we would need vector 2, 3, 4, 5, 6, and 11. So with the information extracted from the sections I noted, then we can continue to build our framework and our software. So let's get going. Okay, so what tasks do we have to accomplish next? First, we have to the creation of the framework for the external interrupt. Then we have to define, we need definitions associated with interrupt service routine, a couple of sample programs, and finally, we need the definition for capture event interrupt. So let's get started with the framework for external interrupts. Now the information here I obtained from the data sheet. And what I'm going to do is I'm going to add the code. Now these codes are pound defined and it's going to allow us access to each of the bits in the register. You can see PCIF 0 is going to have a value 0 which is going to allow us access to the bit 0 of the register, pin change interrupt flag interrupt. So we had 8 registers. I'm counting here for 1, 2, 3, 4, now 5, 6, and this is the code to change to access those bits in those 2 registers. And here we have 7 and 8, and this is the code to access those registers. So let's create the include file. The framework will be implemented as an include file. So this is the include file, and we're going to name it framework interrupt ext. Now the source code is generated by extracting the contents from the column code. To prevent any naming conflict with existing development environments, the parameter names have been modified by adding an X in front of each parameter. So you have all the parameters that were extracted from the column code, and here you have an X in front. The reason we need an X in front is because most of the environments do this work for you. So to avoid collisions, we call it something a little bit different. So now we have our framework done. Next, we have to talk about the interrupt service routine. So what I'm showing here are the information I extracted from the data sheet for that ATMEGA. And what I'm going to add here is a column where I'm going to add the vector names that were going to be used, which are defined in the environment. So we have for the external interrupt request 0, we're going to, it's called int0 underscore vect. For the external interrupt request 0, the int1. Then we have 3 pin change interrupt request 0, 1, and 2, which are called PCINT0, PCINT1, and PCINT2. Now this table also contains the timer 1 underscore caption. Now I put this separately because in the data sheet it's handled separately. So all the definitions for 2, 3, 4, 5, and 6 vectors, we found it on the section for external interrupts. However, the information associated with the timer 1 capture, you're going to have to find it in the timer section, which we'll do later. So now let's go and define all of these 6 vectors, find out what they do. Okay, so the int0 vector is associated with pin D2. So we have pin D2 has an interrupt, we can enable an interrupt called int0, and those we have to hook up to pin 4 to make it work. So let's see how we do that. So first we need to configure the pin 4, which is PD2, to input, because we're going to get an input. Now at this time I would like to note that the pins, by default, the ports I should say, are initialized to inputs. Next, we need to enable the INT interrupt by setting the INT bit in the EI mask to 1. So basically this is telling the processor that we're going to use port D2 as an interrupt, and the name is INT0. Next, we need to define what signal will trigger the interrupt. So a low level, you can configure it so that the low level triggers the interrupt, or we can configure it in such a way that any logic change triggers the interrupt. That would mean the signal from high to low or low to high. And finally, we can trigger the interrupt by falling edge, which means going from high to low. I should have said finally, sorry. Now it's finally. And then we can configure the interrupt to be triggered from a rising edge. That means that we go from low to high. Now, every time we work with interrupts, we must call the global interrupt function SEI. Now, let's see the format for the header for the interrupt service routine. So that would be ISR open interrupt INT0 underscore VECT close parentheses. Now I'm going to have examples with, that is going to show you exactly how this works. So let's go to the next one, which is the INT1. The INT1 is associated with port D3 and pin 5. So let's see what are the steps. First, of course, a port D3 needs to be set to input. Next, we have to let the microcontroller know that we're going to be using the INT1 interrupt, which means that the port D3 is going to be configured to accept interrupts. Next, we need to define what level of signal will trigger the interrupt. As before, it's going to be low, any, falling edge, or rising edge. Next, every time we use interrupt, we must call the SEI, which is the global interrupt functions. And finally, the format for the ISR will be ISR open parenthesis INT1 underscore VECT in close parenthesis. Now let's tackle the PCINT0 interrupt. These are an interrupt that we set them up for all the port B. So when you set this interrupt, then all the pins associated with port B can be configured to be interrupts, react to interrupts. So we would have PCINT0, PCINT1, PCINT2, 3, 4, 5, 6, 7. Okay, so how do we do this? First step, we have to configure the pins B0 to B7 as input. Next step, we need to tell the microcontroller that we intend to use the B ports as interrupt. And next, we need to tell the microcontroller which pins we're actually going to use. So you have the choice of, you can use any of these as interrupts. You can select 1, 2, 3, or you can select them all to be configured to create interrupts. Next, any logical change to the selected port B will trigger an interrupt. So any pin that changes from high to low or low to high will trigger an interrupt, as long as we've configured the pin to be interrupt enabled, and we have we've enabled all the pins to be interrupts. So as usual, we have to call the global function, and the format for the ISR will be ISR open PCINT0 underscore VECT. So if we configure this port B to be to react to interrupts, then any of these interrupts, one or all interrupts, will, every time they get triggered, because there is a high or a low, the signal changes from high to low, they'll all go to this ISR. And part of our job is going to be to figure out which pin triggered if they interrupt, of course, if needed. Next, we have the PCINT1. These interrupts are related to the port C. So we have, and one thing is the name of the interrupt is PCINT8, then followed by 9, 10, 11, 12, 13, 14, all the way to 14, because we have PC6. Now, when we did the port B went all the way to PCINT7, then port C follow with PCINT from 8 to 14. So they are sequential names. So how do we make this work? So the first step would be to set the port C to input. That would be port C0 to PC6, according to which one we want to use, of course. Next, we tell the microcontroller that we're going to be using some of the some of all of the ports C as interrupt, and then next we tell them which ones. Now again, as I noted before, any change in logic will trigger an interrupt. So if any change in the value from of port C from port C0 to port C6, any change in the logical value will trigger interrupt. Next, we always have to call the global interrupt. And finally, as I noted before, the ISR, open parenthesis, PCINT1 underscore VECT, close parenthesis, will be the header for the interrupt service routine. Now, if we configure this to trigger all the PCs to trigger a interrupt, if the value changes, then every time an interrupt triggers, it will go to this service routine. And then it's again our job to be able to figure out which interrupt triggered. That's assuming that's something that you want to know. Now, finally, we have the port D, PCINT2, which deals with the port D. And again, it just keeps the number in PCINT 16, 17, 18, 19, 20, 21, 6, 20, 22, 6, sorry, in port D7, 23. Now let's see how we go about doing this. So first we configure all the pins to inputs. And again, let's remember that by default they are set up to inputs. Next, we tell the microcontroller that we intend to use one or all of the pins port D as with interrupts. Next, we tell the microprocessor which of those pins we'll actually use. Now again, any change in logic in port D from between port D0 to D7 will trigger an interrupt. As usual, we'll have to call the global interrupt function, and the format is going to be ISR open parenthesis PCINT2 underscore VECT. Okay, so we covered all the pins. So all the pins can be configured to be to trigger interrupts if we want to. Now, as I noted, any of those pins you can trigger the interrupt. So it's going to be our job to figure out which actual pin triggered the interrupt. So let's tackle that issue. To check which specific pin triggered the interrupt and determine whether it was rising or falling edge, we have to: 1. Before enabling interrupts, read and store the initial state of the pins in a variable. 2. Once the interrupt triggers, you are inside the ISR routine, read the current state of the pins and compare it with the previous state. The XOR operation can be used to identify which pin have changed state, which is the one that actually triggered the interrupt. So you read the initial state of the pin, you read the final state, figure out which one changed, that triggered the interrupt. Okay, also if the pin value changed from low to high, we can infer that the rising edge triggered the interrupt. The opposite would, of course, would also be true. Okay, let's go to our examples. Okay, what we're going to do here, we have a switch hooked up to port D2, and we're going to configure that to be INT0, to trigger INT0 interrupt. And when we get the interrupt, we're going to turn the light on. If you push the button again, we can interrupt and we'll push the light off. So you can see here, name of the port PD2, we are going to associate an interrupt called INT0. So let's look at the code. So we included our framework, which we developed the last 2 presentations ago. We're going to include our framework port, which we developed the last presentation. And we're going to include the framework interrupt text, which we just developed. So first we initialize the port, like we said. Now this port is already initialized to input by default. But what we need to do is we need to set the port PB1 to output, because we're going to have to output the 5 volts to turn on the light. And then the next thing I do is I use enable an internal pull-up register, which is done like this. So the fact that I enable this pull-up register means that if the switch is open, we're going to have a high signal. When the switch is closed, that's going to go to low. Next, as I noted, we need to something to enable the global interrupt SIE, open parenthesis close. And here I have another signal that I added and I didn't mention it, which is that we should have the capability to disable interrupts also. And that's CLI, open parenthesis, close parenthesis. Now let's set up the interrupts. So there are 2 things that we need to set up on the interrupt. First, we need to tell the microcontroller under what signals is the interrupt going to be triggered. So we have ISC00, ISC01, and both are configured to be 0. This nomenclature we discussed at last presentation. So we do that, which is going to mean that it's going to trigger the low. Next, we have to tell the interrupt that we are going to work with INT0. So we enable the INT0, because we could also be working with INT 1 if we wanted to use another pin. But anyhow, here we decided to use INT 0. Then on the main, we just have the INT, init the ports, init the interrupts, and we're good to go. And we enable the global interrupt, forgot to mention that. So this is where the main program started, and this is where it ends. You can see the close of the, and this is the ISR interrupt. So I noted the format ISR open parentheses INT 0 underscore BEC close parentheses. So here we started. So the first thing I do, I disable the interrupt because I don't want to be another interrupt to trigger while I'm here. Next, I put a 400 milliseconds delay, and that's just it's enough time for this particular button, so we don't get affected by bouncing. So by the time we're out of here, the bouncing should have been done. And then right here, what I do is I take in pin B1, I change it between 1 and 0, which what it does is turns on the switch when I'm the first time. Next time I go into this routine, it turns off the light. So basically, each time I push the button, the light comes on. I push it again, the light comes off. So let's go to another example. So this time we're going to try, we're going to hook up this to PCINT port 9, port 10, PCINT port 12. So that's the C port interrupt. And then I'm going to hook it up to PCINT 0, PCINT 2, PCINT 4, which are the B ports. Now what I want to do is every time I push any of these 3 switches, I'll turn on one light. When I press any of these other switches, press the other light. So just showing that how the interrupt work. So let's go to the code. So the first thing we do is we initialize the pin D2 and pin D3 to outputs. That's pin D2 and pin D2 and pin D3 to output, because we're going to send a signal to turn on and off these 2 LEDs. Next, on port C and port B, I have the pull-up resistors for all the PC C1, C2, C4, C1, C2, C4, and I have B0, B2, and B4, B0, B2, and B4. So now we have all our pull-up resistors. Next, I have a routine for the global interrupt and a routine to disable interrupt. And now here I'm going to go and I'm going to initialize the external interrupt. So what I want to do is I want to enable PCINT 0, PCINT 2, PCINT 4. Here I'm initializing to what? PCINT 0, PCINT 2, PCINT 4 on the mask 0. Now I also need to initialize PCINT 9, PCINT 10, and PCINT 12. PCINT 9, PCINT 10, and PCINT 12. So basically these are the pins that are going to be associated with interrupts. Now next, what I'm telling the processor here is that, by the way, I intend to set up some of the pins in port C and port B to respond to interrupts. Okay, now this is the main program. So I initialize the ports like we have here. Next, we initialize the external interrupts right here that I already explained. And then we enable the interrupt, which is the SEI. So if I press any button in the PCINT PCINT 0, then it's going to trigger this interrupt. Now this interrupt, first thing I do is I disable the interrupt. Then I wait to try to solve the bouncing. But in this case, the button needed some extra work on the bouncing. So I had to do this here, and then I turn on the light. Now here we have the interrupt for the PCINT 1, and in this case I do the same thing exactly. So the idea was the PCINT, the port associated with the port C, and then here we have the register associated with port B, and they get their own service routine. Now, if I needed to find out which of these three ports port C triggered, then I would have to get the initial value of the ports, and then once they here in the interrupt routine, I would have to read the port value again and figure out what changed, and that's the one that triggered the interrupt. So that was the end of the examples. Now let's talk a little bit about the timer capture event interrupt. That's the timer cap vector. So this interrupt is associated with the timer counter. This feature allows the timer to capture the value of the timer counter at the moment the event occurs. So when the event occurs that triggers interrupt, you capture the timer value. Now this is useful for measuring the time between events, such as width of a pulse. So you read, the first time you get a interrupt, you read the timer value, then you wait until you get a second interrupt and you read the timer counter again, and then you compare those two values, and that should give you some information you need for some reason. But that's going to be covered in detail once we get to the timer portion. So anyhow, we got to the end of the external interrupt presentation. We did cover how to put together the framework, and then we talked about the ISR in interrupt service routine. I explained all about the ISR and their functionality, and finally we went through two examples to give you an idea how this works. Anyhow, I hope you've enjoyed these presentations, and next time we'll have the presentation on the Watchdog Timer. Thank you very much.